Okay, this is Jack Jackson. Let's continue with some applications of integrals to economics problems. So economics are a good class of problems to look at. We looked at some other things like motion problems, which of course everyone deals with some kind of motion at some point, and economics is another thing that all people deal with. They deal with money, buying things, selling things, and so forth. So it's interesting to deal with some economics. So suppose the rate of sales of a given product varies with time. Let R of t represent the sales rate. That would be in items per year. Let t equals 0 correspond to January 1, 1995. If we integrate R of t dt from 0 to 1, what does that mean in the real world? So this is kind of a class of problems that you might see sometimes where you just have to interpret what's meant by this. Now, of course, if you think about it in this case, just thinking of the units can kind of help you quite a bit. So the units of R of t are, well, in this case, items per year, and the units of t are years. So when you do R of t times dt, the dt actually has units. They're the units of delta t, or in other words, the units of t. So that is, the dt is units of years, and then the rate, R, is in items per year. So when you multiply that together, you get items. So that gives you some idea right there what you're dealing with when you have this integral. It's going to be items. And of course, the fundamental theorem says if you integrate a rate, that's a derivative then of the number of items with respect to time. So what you get is the total change in items sold. So this is the delta of the items sold for that t equals 0 to 1. Well, t equals 0 to 1 corresponds exactly to the calendar year 1995. T equals 0 is the first day of January 95. T equals 1 is the start of 1996. So that's the 1 year of the full calendar year 1995. And so what this represents with this integral is then the total sales in the 1995 calendar year. The increase in sales from time equals 0 to time equals 1, which is, of course, what they sold in 1995. Okay, let's look at another example here. Recall that the word marginal means derivative. Okay, so let's look at something here. Consider the cost of drilling an oil well. There are two types of costs. There are fixed costs that are independent of, say, the depth of the well. And then there are marginal costs. They're incremented costs that comes from drilling 1 more meter deep. Using both of those, you add them together and you'll get the, well, add them together, the fixed cost plus the marginal cost, and you will, well, that's not right. Add the fixed cost and the variable cost, and you'll get the total cost. Okay? And marginal costs depend on the depth at which you're drilling. So as you go deeper, it gets more expensive per meter as you dig deeper. So we would expect the marginal cost to be an increasing function of the depth. And of course, total cost certainly is increasing as you dig deeper. Now let's suppose the fixed costs are 1,025,000 rials. That's the unit of currency in Saudi Arabia. And the marginal cost are C prime of x equals 4,800 plus 12x. So notice that C prime of x is an increasing function. And then of course C will also be an increasing function, where x is going to represent the depth of the well in meters. So let's see if we can figure out the total cost function C of drilling a well that's x meters deep. Well, anytime you have a derivative of a function, which is a marginal function, in this case the marginal cost, that's the derivative. Anytime we have a derivative function, we want to find the original function C. We're just finding an antiderivative of this. So we need an antiderivative of this function, and of course that's going to be the 4,800 is going to pick up an x. This x here is going to go up to second power, and we divide by 2, which makes it 6x squared. So I wrote it in decreasing order here of powers of the degree of each term there, the powers. So 6x squared plus 4,800x plus some constant C is the cost here. Now notice if you plug in x is 0, you get C for an output. So C is actually the fixed cost, which we know is 1,250,000. And so here's our cost function, 6x squared plus 4,800x plus 1,025,000. The cost then is measured in whatever this rials, the currency of Saudi Arabia. And so if we can plug in the depth here, then we get the cost. For example, if the depth is 0, we're still out this fixed cost, which we have to do before we start drilling anything. And then we also add things as we add to this. And notice both of these, with x being positive, both the middle term and the first term are positive here. So we're adding money to the cost, so the cost is increasing, and the derivative is positive, and the derivative is increasing. So this is an increasing concave up function if we were to graph this. Of course, we could plug in a particular x value and find the cost then that goes with it. Okay, let's try another one similar to this. Let's see if you can do this one. Suppose the marginal cost for a product is C prime of x equals 60 times the square root of x plus 1, and the fixed cost for that product is $358. Let's suppose that the marginal revenue is $86. Find the profit or loss from a production of 8 units. See if you can figure this one out. Come back when you think you have an answer. Press pause now. Well, let's think about this a minute. The first thing is, make sure we understand what these words mean. Profit is revenue minus costs. I guess maybe first we should talk about what those words mean. When we talk about profit and revenue and cost, we're talking about from the producer's standpoint. So cost, for example, is not the cost that the consumer pays for an item. It's how much it costs the company to make the item. Revenue is the total amount of money that they bring in for the item, their total receipts. And so if you take revenue minus cost, whatever's left is profit. So in this context, revenue and cost are always positive or 0, but profit could be positive or negative. A negative profit we would call a loss, and a positive profit would be a gain. And of course, if you're in business, you want a positive profit, and you want that profit to be as large as possible. So notice that we have this relationship here, but profit equals revenue minus cost, or P equals R minus C. And so what we have is P equals R minus C, but that's going to imply that P prime equals R prime minus C prime by the sum rule for derivatives. So in words, what we were saying is marginal revenue minus marginal cost equals the marginal profit. Again, we're using marginal for derivative. So if we integrate marginal profit from 0 to 8, we get the change in profit for 8 units. Okay. If we start out at negative $358 for profit, that's going to be our fixed cost. Okay. So cost at 0 is the same as the opposite of that is the profit at 0. One thing you know about every revenue function is they always start at the origin, because why? If you don't sell any items, if you don't make any items, you're not selling any items, and you have no income. So revenue always starts at the origin. Cost, on the other hand, usually starts positive because you have some fixed costs that don't depend on the number of items. This might include things such as research and development and other things that don't depend on the amount of items that you're making. Well, let's see what we've got here. So if we integrate the profit function, well, what is the marginal profit function? So let's see, we have R prime is 86x, C prime is 60 times the square root of x plus 1. So R prime minus C prime is 86x minus 60 square root of x plus 1. So that's what I have right there. That's the marginal profit function. It's marginal revenue minus marginal cost. If we integrate that from 0 to 8, we'll have the change in profit. So we'll have profit 8 minus profit 0. If we add on profit 0, or if we subtract profit 0 from that, then if we add on profit 0, we will get the profit at 8. Well, the profit at 0 is negative 358. So we just get this here. And again, if we just want an approximate value, we can do this in the calculator here. And notice I'm integrating, then subtracting outside the integral there. And this works out to be around $1,354. Okay? So $1,354 is the profit from producing and selling 8 items. Try another one kind of like this yourself. The marginal cost from the product is, I've seen this, I don't particularly like this notation. I'd rather use C prime of X, but some books I've seen write it as MC bar or MC for marginal cost. And this one is, again, the same thing, 60 square root of X plus 1. And this time I got a slightly different fixed cost, 378, and a slightly different marginal cost, 84X. This time find all of these things, the cost, revenue, and profit functions, and the profit or loss, or gain or loss, the profit from a production of 8 units. Press pause now. Okay, now that you're back, hopefully you've tried this one. The marginal cost, which is C prime of X, is 60 square root of X plus 1, or 60 times X plus 1 to the 1/2. The fixed cost, or C of 0, which is 378. The cost is then the fixed cost plus the change in cost from 0 up to X. So it's the integral from 0 to X of C prime of T dt. That's the additional cost for making X items. Okay? But then they have the fixed cost on top of that. Or another way of looking at this integral, according to the fundamental theorem, it's C of X minus C of 0, and if you add that to C of 0, the C of 0 and the minus C of 0 cancel, and you just get C of X. So, or in other words, this is just the fundamental theorem, just solve for C of 0. C of X minus C of 0 equals this integral. Add C of 0 to both sides. So a couple different ways of saying the same thing there. Put in the value of C prime of T, the formula, and then we want to integrate this. Now factor the 60 out front. Think of U as T plus 1, du is dt, so I can do the substitution there. Hopefully it's obvious what U is. U is T plus 1. And so this goes up to U to the 3/2, multiplied by the reciprocal of the 3/2, which is 2/3. Let's see, 60 divided by 3 is 20, times 2 is 40. And we want to evaluate from T equals 0 to X. So first of all, I need to substitute in, and by the way, this should say T equals 0 to T equals X, not U. I'll fix that later. And then, let's see, so these are T values, which I do have marked here, T equals 0 to X. And so I had to switch back to T's. There, I did it. And plug in X and 0. So let's see. Let's do this part first. 0 plus 1 is 1 to the 3/2 is 1. So this is just minus 1. I distributed the 40 times that minus 1, gave me the minus 40 here. I have 40 times this part right here, and I take the minus 40 and the 378 put together is 338. So the cost is 338 plus 40 times X plus 1 to the 3/2. And so if you plug in 0, let's see, 0 plus 1 is 1 to the 3/2 is 1 is 40. 40 plus 338 is 378, which is a fixed cost. And then, of course, this function increases from there. That's the cost function. Now, the revenue function is similarly R of X minus R of 0 is the integral from 0 to X of R prime of T dt. Subtract R of 0 from both sides, but R of 0 is just 0. We know that R of 0 is 0. R of 0 equals 0 for any revenue function. I explained that just a minute ago. R prime of T is given to be 84T, right here. And so this goes up to t squared for the antiderivative divided by 2. 84 divided by 2 is 42. And evaluate that from 0 to x. So that's x here, and then back to the 42 out. Then I get x squared minus 0 squared. So that's just r of x is 42x squared. Of course, put in 0, you get 0, which is what you should have. And of course, this is going to increase from there on. Of course, the domain, of course, of these is implied that x has to be 0 or positive because you can't make a negative number of items. X represents number of items. So that's implied in both of these. The profit then is just revenue minus cost, so that's 42x squared minus this one here. And if I distribute the minus, well, I don't have to distribute the minus, I can leave it. P of x is 42x squared minus, parentheses, 338 plus 40, x plus 1 and 3 halves. And then if I want to find the profit of 8 units, I can just plug in 8. Or any other amount, I can just plug it in here. 8 plus 1 is 9, square root of 9 is 3, 3 cubed is 27, 27 times 40 plus 338. We're going to subtract that from 42 times 8 squared, and that does turn out to be positive $2,986. So they have a positive profit at that point. They have gained money. Let's see here. Okay, let's do another one here. Throughout the 20th century, the yearly consumption of electricity in the U.S. increased exponentially at a continuous rate of 7% per year, or at least it can be modeled by that. Assuming electrical energy consumed in 1900 was 1.4 million megawatt hours. First of all, write an expression for electricity consumption as a function of time t measured in years since 1900. See if you can do that one first. Press pause. Okay, when you have something growing at a constant percentage rate, that's an exponential function. One of the basic things we should know about types of growth from our algebra classes. And since this is a continuous rate, this is a formula of the function some constant, some initial value times e to that kt, and that percentage rate is k. So k is 7% per year, so that's 0.07 t. So t must be in years since that rate is per year. And the initial amount is 1.4, so when you plug in t as 0, this is 1.4. T is measured in years since 1900, and so that's the formula that we were looking for. Find the average yearly electrical consumption over that century. Not this century, but that century, meaning the 20th century. Okay, press pause. Worked it out. Okay, hopefully you got this worked out. Remember to do the average value of a function. It's 1 over the length of that interval, 1 over b minus a times the integral from a to b of that function. So we have the energy consumption here is 1.4 e to the 0.7 t, and we integrate from 0 to 100, and then this is 1 over 100 minus 0, so that's 1/100th, the integral from 0 to 100. So to set this up, I'm going to let u be 0.07 t, and du is then 0.07 dt. So I need to balance that by dividing by 0.07. I put the 1.4 out front. Turns out if you take 1.4 divided by 0.07 and divide by 100, you get 0.2. And so we're integrating from t equals 0 to t equals 100 of e to the u du, so that's just 0.2 out front, and then e to the u, evaluated from t equals 0 to 100, and so we need to switch to t's, so u is again 0.07 t, and now we can substitute in 100 and 0. I can leave the 0.2 factored out front. 0.07 times 0 is 0, e to the 0 is 1, so that's where the minus 1 comes from. 100 times 0.07 is just 7. So what we get is 0.2 times parentheses e to the 7th minus 1, or in other words, approximately 219. And the units are the units of whatever E is, and that's million megawatt hours. Of course, we didn't have to do all this and find an actually antiderivative since we needed a decimal approximation, we might as well have just done it on the calculator, and that's the wrong calculator screen for this one. So let me put in the correct calculator screen for this one. Okay, so we just, oops. So we just do, let's say math 9, and just pretty much put it in. Oh, actually before that, I need 1 over 100. 1 over 100. Now that's times the integral, math 9, from 0 to 100. Of, now put in our formula here, 1 point four times e to the power 0.07 x, and that's with respect to x, that blank, or enter it in like this in the older operating system. I brought the 100 inside. I could have left it outside. In fact, I am going to write it outside. But of course, the constant multiple rule says it can go either way. And when I do that on the calculator, this is what I get. About 219. And of course, here, let me do this. If I do this, 0.2 times parentheses e to the power 7 minus 1. Notice I get the same thing. So either way I go at that, I'm going to get the same decimal. And since I want a decimal, might as well just use the function integrate, although this certainly gives us some good practice with antiderivatives to do it this way up here using the fundamental theorem. So in other words, this basically uses Simpson's rule or something similar to that. In what year was electrical consumption closest to the average? And can we predict ahead of time if it's the first half or the last half of the century? Well, what we're wanting is we this 219.12, etc., should be about the same as the function here. I probably shouldn't have rounded this off. So I probably should have used more digits here, or even used the exact value, 0.2 e to the 7th minus 1, and found when these two are equal to each other. And it's approximately 72. Or another way to do it is to, on the calculator, put the function in here and put the value here, the y value that you want it to be, 219 again. It'd be better if I put more digits there. Find an appropriate window. We're going from 0 to 100 for the x's. I could look in and see this function increases, so I need put in 100 here. I get 1.4 times e to the 7th. I need to go a little bit beyond that. About 1550 is good enough. And graph that, and then calculate the intersection point, and that's the x value I'm looking for. So if I graph this picture is actually telling. because the actual electrical consumption on this is the amount of energy consumed is the area under this this exponential curve here. That's the total area. Well, the area under this horizontal line, that rectangle, that area is the same. Now, since this is an increasing concave up function, you'd expect these to cross in the second half of this interval closer to the right side than you would the left. If you were way over here on the left, you wouldn't get hardly any area at all. If you're too far to the right, of course, then you would get too much area under the rectangle, but you'd expect it to be over halfway, and sure enough it is. It's in the second half of the century. Next video, we'll talk a little bit more about some economics problems dealing with total, present, and future value of an income stream.